So you're looking at implementing a finite state machine in Godot, and maybe you've run into this question before. Maybe like Gamester, you've wondered, do I have to use nodes in Godot for a finite state machine? Is there really no other way? Well, after seeing this comment, I did a little digging, and it looks like the information for this on YouTube is pretty sparse. And that's what inspired me to create this content and put this information out here. Now, I just want to say, using nodes is not a wrong way of doing things. The information that I'm presenting here isn't the de facto right way to do it, and it's not a dig at other tutorials that do use nodes. It's really great information, and it's really up to you as a developer to choose which you feel is right for your project. With that said, let's take a look together at what the structure might look like if you were to do a finite state machine in Godot without using extra nodes. First, to make sure everybody's on the same page, let's talk about very quickly what even is a finite state machine. A finite state machine is simply a design pattern. It is meant to keep logic relating to some aspect of your total state machine separate from all other states, so that you can easily switch between logic, easily debug where problems are, and makes it very easy to add new states and new logic to switch between. The context that we'll be looking at a state machine in for this project is player movement. So we're going to focus on the states idle, run, move, and jump. So like I mentioned, nodes are not a wrong way of doing things, and doing a state machine without nodes is not necessarily the right way to do things. There are pros and cons to both. Using nodes, you'll be able to very easily visualize and see what states are available right within the Godot editor. That does mean that each state gets a scene and a node, maybe some scripts, and you can clearly see that separation of logic. It's a very visual way of doing things. However, that does add more nodes to the tree, and that can lead to complexity and performance issues depending on if you're doing, say, 1,000 enemies and each enemy has X number of states, and those states each have a script attached to them, and not all of that's being tracked in the tree. That can really slow things down. It also requires managing of all of those child nodes in that visual way, so a lot of drag and dropping, a lot of physically moving things around. And it requires a bit more boilerplate to get all of that working. But when we look at classes, in my opinion, things are cleaner and more compact. It's definitely faster to write and tweak. And you can take this more generic implementation and you can apply it to other engines, other application types, and other languages. Now, there are downsides to this. It is not as visual. It is not as easy to see in the Godot editor when you do things this way. It requires a bit more manual management of states, especially moving from one state to another. And if you build your classes to be too bulky, it can definitely get a little bit messy, which is also true for nodes. So just keep things simple, keep things focused, keep each state responsible for really one or two, preferably one specific thing. Now that we've talked a little bit about the pros and cons, let's take a look at the player class of the state machine. This is kind of the controller for the state machine. We start by defining an enum, which is just a series of named values. I like doing things this way rather than using hard-coded strings. It's more structured. We then use those enums as a key into a dictionary that we will then populate with a pairing of enum values to our different state classes. The benefit of using a dictionary is that it's super fast, it's incredibly structured, and we can make sure that we always get the same state given a specific input. In other parts of the player class, we will also call for whatever current state we are in, the applicable functions. And we'll take a look at what those functions are in the next slide. But if you look in physics process, you can see that we are calling the current state's physics process. And we also have a function called change states, wherein we call the exit and enter states for both whatever state we're in and the state we're moving to. As a side note, we would also, in the process function, and I just don't have it defined here, but we would also call the state's process function. Let's take a look and see how that's structured. So this is the base state class. this class is never really meant to be used other than being inherited by the specific states that we'll be implementing. So you can see we have a series of functions that have zero functionality to them. They do absolutely nothing. We do pass into each of these functions a reference to the player class, and we'll see why that's important in a moment. But the reason we do this is so that each state that we implement can choose whether or not it wants to actually implement the logic for these functions. So you'll see that most of our states, the only thing we implement is the physics process, and we leave most everything else alone. There is one state where we actually use the enter state as well, but this is up to each specific state to choose whether or not to implement this functionality. But we always want to guarantee that there is some kind of implementation for it. The default implementation for each of these things will just be to do nothing. So let's see how that actually works in our very first state, which will be the idle state. In the idle state, you can see us using that player reference on a few lines to call the change state function. This is how we actually tell the state machine when and to what state to change to. So there are a few ways that you can decide as the developer on how your states are going to affect things. You can either make it to where each state has complete and total control over the player controller, or you can make it such that each state is responsible for managing a certain aspect of the player controller. In this specific example, we are simply making it such that each state affects the acceleration for the player, and the player class is responsible for using that acceleration to affect its velocity and then to actually move the player. So the idle state, the only thing that we're really doing here is looking to see, hey, is the character on the floor? If it's not, we must be falling. Or has the player pressed right, left, or jump? And if they have, let's make sure we move to the applicable state for that input. So here we can see the idle state can actually only move to 3 other states. It can only move to fall, to the move state, or to the jump state. The next state we've implemented is the fall state. So similarly, the fall state can actually only move to the idle state. There is some logic in here for moving the player's acceleration left or right, but we're not actually going into the movement state. This is just a specific thing we can do in fall, which is control the direction we're falling with the movement keys. The only other state we can actually go to is the idle state, which you can see in the else clause. And I think this is a good time to point out, just like the decision as to how much each state controls, it's also a decision for you as the developer to decide who is responsible for switching from one state to another. And what I mean by that is, in this example, it is the responsibility of a state to choose when to go to another state. But you could also implement this where the player class, the sort of base state machine, is what decides when to move to different states. And it's really up to you and your project in terms of which one is going to be better. Because this example is so simple, it made a lot of sense for each state to be able to choose when to move to another state. If you have more complicated movement, maybe you're able to cling onto objects, or maybe you're able to swing from one thing to another, it might actually be better for the state machine itself to choose when it can switch states and how it switches states. And also for something more complex like that, it may be better for the states themselves to manage everything about movement, especially if when you are in one state versus another, the entire way your character will be moving is different. For these really simple examples, the character is kind of always moving in the same way. It's really just what direction are we moving in versus changing how things work entirely. You can mix that responsibility. I would be cautious in doing that though, because it might make things a bit more difficult to debug if something is not behaving the way you expect it to. The more simple you can keep your structure, the more simple it will be to find issues that arise while you're testing. We've really talked about the bulk of a state machine at this point, so the move state, there's not really a lot of new information here. We're just kind of doing the same thing that we've done in other states. And that's a really nice place to be. If with just a few examples we can already see the power and flexibility of a state machine, and we don't have to define a bunch of different classes. So here, our movement state is basically, are we on the floor? If not, we must be falling. If we are on the floor, move left and right with our input. And if we jump, go to the jump state. If we're not doing anything, we must be idle. Very simple. Let's take a look at the jump state, because it's going to have a few interesting details that we haven't looked at yet. So here you can see the jump state specifically has some variables of its own. So it keeps track of the jump time, how long a jump sort of takes, and the current jump time, how long we've been in the jump state. It also makes use of the enter state to reset that jump time every time we go into it. Otherwise, same deal. In the physics process, we're checking for some conditions. Is the current jump time greater than or equal to our max jump time? And has the player hit their head on a ceiling? Or specifically, have they not? If the current jump time is not greater than the jump time and we haven't hit our head on the ceiling, go ahead and keep accelerating in an upward direction. Let the player control their jump with left and right and increase that jump time. There's also an if we've stopped pressing the jump button, leave the jump state, so we can actually control how long we jump. The longer we hold the jump button down, the further we jump. If none of that is true, then we must be falling. And we've been in the jump state, so we must have had some kind of upward movement based on the way that we've implemented this. And so the only state that a jump can end in is the fall state. And that's really it for implementing a state machine in Godot without using nodes. Notice we didn't have to create any special nodes, we didn't have to manage anything visually, it was all done with logic, and it was done with relatively small amounts of code. It really doesn't take much to create and use a finite state machine, and it really is up to you as the developer to decide those implementation details that we talked about before. If you have questions, definitely feel free to leave a comment. I'll do my best to answer them. If you are reading through the comments and you see a question that you believe you have the answer to, don't be shy. Feel free to share your knowledge. If you're interested in the code, I will have a link in the description to the GitHub repo where this really simple project lives, so you can download it and run it yourself. This is on Godot 4.4. And I'll also make sure to put a link to this specific presentation in the comments as well if you're interested in that for any reason.